In the last lecture, we introduced two important notions. The first one was the notion of linear combinations. As a consequence of this led us to the notion of linear independence. Let us recall the definition of linear independence. Suppose V is a vector space over F. F can be any field. So, suppose V is a vector space over F and we have a finite set U1, U2, etc., UR, a finite set in V. Then we say S is linearly independent. As I mentioned last time, we will write Li for linearly independent. We say S is linearly independent whenever we have a linear combination of these vectors giving rise to the 0 vector, then all the coefficients must be equal to 0. This is the same thing as saying that the only way to get the 0 vector as a linear combination of the vectors in S is the so called trivial linear combination. So, that is only trivial linear combination of S vectors or the vectors in S can yield the 0 vector. If the set is not linearly independent, it is said to be linearly dependent. So, S is said to be, we will write LD for linear dependent. So, it is said to be linearly dependent if S is not linearly independent. What does that mean? A set is linearly independent if only trivial linear combination will give 0 vector. So, not linearly independent means non-trivial linear combinations should also yield 0 vector. That is, non-trivial linear combinations of S vectors will yield the 0 vector. What does that mean? We must have a linear combination in which all the coefficients are there, at least one of them should be non-zero. So, there exists alpha 1, alpha 2, alpha r, at least one of which is not equal to 0, and the linear combination alpha 1 u 1 plus alpha 2 u 2 plus alpha r u r gives the 0 vector. So, thus when you say linear independence, whenever linear combination is 0, all coefficients must be 0. When we say linear dependence, there can be a linear combination which is the 0 vector without all the coefficients being 0. Now, let us look at one simple property of the linearly dependent vector. Suppose S is linearly dependent. This implies 1, just as we observed above, there exists alpha 1, alpha 2, alpha r, at least one of which is not 0, such that this linear combination is 0. So, let us say that alpha j is not 0. So, there exists alpha 1, alpha 2, alpha r, at least one of which, say alpha j, is not 0. So, that is the first thing that we notice if S is linearly independent. Now, suppose X is a linear combination of S vectors. What does that mean? We must be able to express x as a linear combination of the vectors in S. That means, there exists beta 1, beta 2, beta r, all these scalars are from the field F, such that x is beta 1 u 1 plus etcetera beta r u r. Now, note, when we said that there exists alpha 1, alpha 2, alpha r, at least one of which is not 0, such that what? Such that the 0 vector can be obtained as this linear combination. This is what is meant by linearly. So, this is obtained by the notion of linear independence. Now, suppose we have a vector x which is a linear combination of S vectors, then it can be expressed as beta 1 u 1, beta 2 u r, u 2 beta r u r. Now, if we add this representation and this representation, the left hand sides add up to x, because theta v plus x is x, and the right hand side add up to alpha 1 plus beta 1 into u 1 plus alpha 2 plus beta 2 into u 2 alpha r plus beta r into u r. So, let us call this as gamma 1 u 1 plus gamma 2 u 2 plus gamma r u r, where gamma I is alpha I plus beta I. Since we have assumed that this alpha j is not 0, since we have assumed that this alpha j is not 0, we will have gamma j equal to alpha j plus beta j. Since alpha j is not 0, this cannot be beta j. What does that mean? We have one representation of x as a linear combination of u 1, u 2, u r. We have now another representation of x as a u 1, u 2, u r. In these two representations, the beta j is different from gamma j, and therefore, they are two distinct representations. This means, x has at least two representations as a linear combination of the S vectors. So, this says x has at least two representations as linear combination of S vectors. Thus, whenever we have a linearly, so what is the conclusion? Whenever we have S is linearly dependent, means every x which is a linear combination of S vectors has at least two representations as linear combination of S vectors. So, linear dependence brings in certain amount of vagueness, because there is a lot of redundant information. We shall first look at some examples of this notion of linear dependence and linear independence. First, let us take V to be our standard R3, and let us take the S to be the set of 3 vectors u1, u2, u3, where u1 is the vector 1, 1, 0, u2 is the vector 1, 0, minus 1, and u3 is the vector 0, 1, minus 1. Let us now see whether this set is linearly independent. For this, we must check whether if a linear combination vanishes, does it imply all the coefficients are 0. So, let us start with a linear combination alpha 1 u 1 plus alpha 2 u 2 plus alpha 3 u 3. Suppose this is the 0 vector, what does that imply? Let us find out what alpha 1 u 1, alpha 2 u 2, alpha 3 u 3 is. So, we have alpha 1 u 1 will give me the first entry as alpha 1 plus an alpha 2 here and there is nothing here. So, the vector I will get on the left hand side is alpha 1 plus alpha 2 and the second component I will get as alpha 1, 0 and alpha 3. So, I will get an alpha 1 plus alpha 3. Similarly, I get the last as minus alpha 2 minus alpha 3. This is what the left hand side is. The right hand side is the 0 vector. So, that must be equal to theta 3, which is 0 0 0. Now, comparing both sides, we get alpha 1 plus alpha 2 is 0, alpha 1 plus alpha 3 is 0, minus alpha 2 minus alpha 3 is 0, and this automatically implies alpha 1, alpha 2, alpha 3 are all zeros. So, thus a linear combination can yield the 0 vector only if all the coefficients are 0, that says the set S is linearly independent. Let us look at another example. Again let us take V to be the vector space R 3. Now, let us take again S to be a set with 3 vectors u 1, u 2, u 3, where u 1 is as before, u 2 is as before. Let us now take u 3 to be 3, 2 minus 1. We see that we can easily check, and we had done it in the last lecture, we can easily check that 2 u 1 plus 1 u 2 plus minus 1 u 3 gives us the 0 vector. And therefore, we have a linear combination in which we have non-zero coefficients and still that yields the 0 vector. Whenever such a non-trivial linear combination yields the 0 vector, we know the set is called linearly dependent. So, that says S is linearly dependent. Let us look at another example. Let us take the vector space V to be the vector space of all polynomials in lambda with coefficients from the field F. Let us take the set S to be consisting of the 3 polynomials P 1, P 2, P 3, where P 1 lambda is 1 plus lambda, P 2 lambda is 1 minus lambda, P 3 lambda is 1 plus lambda square. So, we have the vector space of all the polynomials. We have taken a set of 3 vectors. So, we have a finite set of vectors. These are the 3 polynomials. Vectors here are polynomials, because this vector space consists of polynomials. Now, suppose a linear combination alpha 1 p 1 lambda, alpha 2 p 2 lambda, alpha 3 p 3 lambda gives us the 0 polynomial. What does that mean? If we substitute for p 1 lambda and p 2 lambda, let us collect the constant terms first. Alpha p 1 will give me an alpha 1, alpha 2 p 2 will give me an alpha 2, alpha 3 p 3 will give me an alpha 3. So, the constant term will be alpha 1 plus alpha 2 plus alpha 3. Now, let us collect the lambda terms. Alpha 1 p 1 will give me an alpha 1, alpha 2 P 2 will give me an minus alpha 2, alpha 3 P 3 will give me an alpha 3. So, we have alpha 1 minus alpha 2 plus alpha 3 into lambda, and if you now collect the lambda squared terms, it comes only from P 3. So, we will get alpha 3 lambda squared, and that is 0. Since this is the 0 polynomial, the the 0 polynomial, all coefficients must be 0. So, that says alpha 1 plus alpha 2 plus alpha 3 is 0, alpha 1 minus alpha 2 plus alpha 3 is 0, and alpha 3 is 0. Now, if we use the fact that alpha 3 is 0 in the first two equations, we get alpha 1 plus alpha 2 is 0 and alpha 1 minus alpha 2 is 0. Now, it is clear that the first two equations imply alpha 1 is 0, alpha 2 is 0. So, we get alpha 1 equal to alpha 2 equal to alpha 3, all of them 0. So, whenever a linear combination of P 1 P 2 is 0, then all the coefficients must be 0. This means the set S is linearly independent. And one final example, again let us take the vector space V to be the space of all polynomials. Again let us take S to be P 1, P 2, P 3, where now P 1 lambda is 1 plus a lambda, P 2 lambda is 1 minus a lambda, and P 3 lambda is say 3 plus a lambda. Again, as we had done in the last lecture, it is easy to check that 2 P 1 lambda plus 1 P 2 lambda plus minus 1 P 3 lambda is the 0 polynomial. This means we have non-trivial linear combinations which give rise to the 0. Whenever this happens, we say that the set S is linearly dependent. So, now we have seen some examples of what it means to say when a set of vectors, a finite set of vectors is linearly independent. In order to show that something is linearly independent, we assume a linear combination to be 0 and then we try to conclude that all the coefficients must be 0. In order to prove something is linearly dependent, we try to produce non-zero coefficients with which we can form a linear combination of the given vectors to produce the 0 vector. We now move on to introduce a very important concept of subspace of a vector space. Let us begin with a vector space V over a field F. This will be always at the background, because as I said last time, this is the universe in which we work. The universe in which we work is always a vector space over a field F. We get into the concrete situation by choosing V to be specific and F to be specific. But when we develop general theory, it will be for a general vector space V over a general field F. So, let us take a vector space V over a field F and let us take a finite set U 1, U 2, U r, a finite set in V. Now, we have seen in the last lecture that when we try to build newer vectors starting from the S vectors, when we say build using the operations of addition and scalar multiplication, precisely we get the linear combinations of the S vectors. So, the vectors that we can build using the addition and scalar multiplication on the S vectors are precisely the linear combinations of S vectors. So, what we do is we collect all those people whom we can build using these S vectors. So, let LS denote the collection of all linear combinations of S vectors. So, what do we have? We have LS is equal to all those vectors in V such that vectors which can be expressed as linear combinations of u1, u2, ur. So, they are linear combinations, all these coefficients must be in F. So, we collect all the linear combinations of the S vectors, and these are the fellows whom we have built using the S vectors. Note, we had observed that the 0 vector can always be obtained at the trivial linear combination of any finite set of vectors, and therefore, the theta vector will always belong to this collection of linear combination of S vectors. Secondly, if you take ui in S, so any one of the S vectors, then we can write it as 0 u1 plus 0 u2 plus etcetera plus 0 ui minus 1 plus 1 times ui plus 0 ui plus 1 plus 0 ui plus 2 plus etcetera plus 0 ur. In other words, a linear combinations in which all the coefficients except the ith coefficient are 0 and the ith coefficient is 1, and therefore, that says ui is a linear combination of the S vectors, and therefore, ui must be in that collection. So, therefore, every vector in S, so that means S is contained in LS. Every vector of S is a part of this collection of linear combinations of S vectors, and therefore, S must be a part of LS. So, these are two simple observations. So, now what have we achieved? First, we had this vector space V, in that there was this small finite set S. Using that set, we have built a bigger set called LS. So, we had the big vector space, inside that a small collection of sets S were given. Using that small collection of sets S, we have built a large number of vectors, and these are the linear combinations of the S vectors. We have put them together when we have got the LS. Now, suppose I think of the LS vectors as building blocks now. We started with the S vectors as the building blocks, and we built LS. It is like starting from the elementary particles and building the atoms. Then we put the atoms together to get some molecules. Now, we want to see whether we can put the LS vectors to create anything new. So, can we use LS vectors as building blocks and build more new vectors? So, we want to see how far we can push starting from S, how much we can build, how big a structure we can build. So, what do we mean by this question? We mean, now take, here is your LS which you have built. In this LS you pick a small finite subset. So, let S1 be a finite subset in LS. Now, go through the building construction starting from S1. So, now use S1 to build. When we start with S, what we built was LS, the collection of all linear combinations of S vectors. So, when we start with S1, we will build LS1, which is the collection of all linear combinations of S1 vectors. So, let us again look at the picture. We had this huge space V. Inside that huge space V was this finite set S, and starting from this finite set we constructed the LS. Now, in this LS again we picked up a small set S1, we are now constructing the LS1. If by chance LS1 takes us outside LS, then we would have constructed more new things, but if LS1 falls within LS, then we would not have constructed anything new. So, we want to investigate, does LS1 have vectors which are not in LS? If it is so, then we could have continued our building process with this various subsets of LS. Now, let us look at the answer to this question. Suppose S1, remember S1 is a finite set sitting inside LS. So, S1 is a finite set. So, remember there is a finite set. So, let us write that set, let us call it as V1, V2, some Vs. So, S1 is a finite set and it is sitting inside LS. Now, we are trying to build things out of this. So, suppose X belongs to the thing that we have built from S1. What have we built from S1? LS1. So, suppose something is in this LS1, what does that mean? LS1 is the collection of all the vectors which are linear combinations of S1 vectors. LS1 is the collection of all linear combination of S1 vectors. So, therefore, any vector in LS1 means X is a linear combination of S1 vectors. What does that mean? That means we can write X as alpha 1 V1 plus alpha 2 V2 plus alpha S Vs, where these alpha i's are all in F. This is because S1 consists of these vectors V1, V2, Vs, and X is a linear combination of the S vectors. But now, where is this V1? V1 is sitting inside LS, but LS is the set of all linear combination of S vectors. So, V1 is sitting inside LS, anything in LS is a linear combination of S vectors. So, V1 is a linear combination of S vectors. Similarly, V2 is a linear combination of S vectors, Vs is a linear combination of S vectors. So, let us keep this as 1, but Vi belongs to LS implies Vi must be a linear combination. How do we write it? Beta 1 U1 beta 2 u 2 plus beta r u r. The S vectors are u 1, u 2, u r, and V I must be a linear combination of this. Since we are talking of the ith vector, we will put a superscript here to say that that is the coefficient of the ith vector, and we can do this for every one of the i's from 1 to s, because there are s. Now, if we substitute all this in the equation 1, what do we get? We will get x equal to alpha 1 into a linear combination of the u 1s plus alpha 2 into a linear combination of the u 1s, and so on and so forth. Therefore, if we combine the u 1 terms, combine the u 2 terms, we will get finally only a linear combination of the s vectors. So, let us do this in a slightly shorter notation. We have x is equal to sum, we will use the summation index, j equal to 1 to r, 1 to, I am sorry, this is now s, because now we are in the S1 set. So, we have alpha j V j. So, the equation that x is a linear combination of the V 1, V 2, V s, we have written it in the short form as j equal to 1 to j alpha j V j. Now, we have observed that V j itself can be written as a linear combination of the, let us write it as j k equal to 1 to r. We want to look at the jth vector. The jth vector will have a linear combination representation as b j 1 u 1, b j 2 u 2, b j r u r. So, we can write this x's in this form. Now, combining these or interchanging the summation notations, we get k equal to 1 to r, summation j equal to 1 to s alpha j into u beta k j into u k, which says that this is equal to, we can write it as some k equal to 1 to r. This whole thing in the inside summation, we can call it as some gamma k u k, which says x is a linear combination of s vectors, which means x belongs to Ls. So, what is the impact of all this? What we have shown is that you start with S, then you build Ls, inside Ls you pick a small S1 and you try to build LS1, LS1 does not go outside Ls. Whatever vector in x in LS1 you chose, that goes back to Ls. So, any vector L x in Ls1 must be in Ls. So, conclusion is that Ls1 is contained in Ls. So, what does that all mean? We started with S, we constructed Ls, then from Ls try to construct Ls1. How did we construct this? Choose a S1 which is in Ls and try to construct the linear combination of S1, it pulls you back to Ls. Ls1 is contained in Ls. So, in other words, this construction process, this building process saturates at the Ls level. So, the building process as saturated at the Ls stage, which means that starting from any finite site S in V, the logistic collection that you can build out of this S is precisely LS. So, starting from S, a finite set S, the maximal construction or building we can do. When we do construction, we use only the operations of addition and scalar multiplication. That we should keep in mind, because the vector space there is nothing else we know. We know that only the addition and the scalar multiplication make the axioms of the vector space. So, the maximal construction that we can do is LS. The reason was the construction got saturated. What makes this saturation? What makes this saturation happen? Now, if we try to construct, the only things that we will do is, again I repeat, addition and scalar multiplication. But if we take the LS and if you take any two vectors in LS and you try to add them, you are going to get a vector back in LS, because linear combination plus linear combination is again linear combination. Similarly, if you take a vector in LS and scalar multiply it, again it is going to be in LS. So, these two basic construction operations do not take you outside LS at all, whatever construction you make, and therefore, you are always in LS. So, the reason for this is, the reason for this saturation they are twofold. One, addition of any two vectors in LS again yields a vector in LS. And the second reason is scalar multiplication of a vector in LS again yields a vector in LS. So, thus there is a certain amount of solid wall created about LS that you cannot penetrate out of the wall by using these basic operations of vector space, addition and scalar multiplication. So, we simply say LS is closed with respect to addition and scalar multiplication. You can't open the door and get out by using only scalar multiplication and addition. This leads to the following notion of subspaces. This leads to the following definition. Any such collection which is closed in this sense with respect to this addition and scalar multiplication, or which is saturated as far as construction is concerned, you try to do anything out of them, you will be still there, you will not be constructing anything new. So, we have this following definition. Let V be a vector space over a field F. Now, we are going to replace LS by a general set. Let W be a subset of V such that 1, remember LS had lots of vectors, the 0 vector was in LS because the 0 vector can be written as the linear combination of any set, and we also had every S vector was already in LS. So, LS contained quite a few vectors. So, it was non-empty. So, we would like W to be non-empty. and the LS was closed with respect to addition, that is addition did not take us out of LS. Similarly, if we are in W, if we take any vectors, the sum must also be in W. We say W is closed under addition. And the third reason for is the other reason for the saturation, namely closed with respect to scalar multiplication. That is, if we take any vector in W and if we take any scalar and look at the scalar multiple, that must be again in W. We say W is closed under scalar multiplication. So, if we start with a set in W which has these three properties, namely that it is non-empty, it is closed under addition and it is closed under scalar multiplication, then we say W is a subspace of V. So, to make a subspace, first we need a non-empty set, and the non-empty set should be rich enough to contain all additions, all sums, that is, if you take any two vectors in that collection, the sum should also be there, and it should be rich enough to contain all scalar multiples. That is, if we take a vector there and multiply it by any scalar, and the result must be. So, it must be a fairly rich collection of vectors. We will make one or two simple observations about subspaces. So, first a few remarks before we see some examples, we will make some remarks. The first thing we observe is that suppose W is a subspace of V. If W is a subspace of V, the first condition for being a subspace is that it should be non-empty. What does it mean to say that W is non-empty? There must be at least some vector in W which says W is non-empty, which means there is at least one vector x in W. If there is a vector in W and if I multiply it by any scalar, it should be in W, because a subspace is closed under scalar multiplication. So, if I multiply by the number 0 or the scalar 0, that must also be in W, since W is closed under scalar multiplication. But 0x, it is an exercise to verify that 0x is nothing but the 0 vector that belongs to W. So, therefore, what we see here is that 0 vector, whatever subspace we have, 0 vector must belong to it. So, the conclusion is that theta V belongs to every subspace of V. And therefore, hence if a subset W of V does not contain the 0 vector, if a subset W of V does not contain the 0 vector, it automatically fails to be a subspace, because we have just seen, in order to be a subspace, first of all every subspace must contain the 0 vector. Then since it does not contain the 0 vector, we can conclude W is not a subspace. So, any subset which does not contain the 0 vector fails to be a subspace. On the other hand, just because some subset contains the 0 vector, it does not make it a subspace, it is only a minimal requirement, that is all. On the other hand, if a subset W contains the 0 vector theta v, it does not necessarily mean W is a subspace. The second remark that we would make is the following: we want to construct a subspace, we want to look at a subspace. Now, what are the things that we have to make sure? First of all, we must take some vectors because we want a non-empty set, and we want to make sure that addition takes you back to that set, scalar multiplication takes you back to that set. So, the safest way to do it is take everybody, every vector in the set V you collect, so that we know that whatever vector in V you choose, their sum is there, the scalar multiple is there, that is the axiom of the vector space, and therefore, V is a subspace of itself. This is like constructing by a very safe way, that is, do not leave anything and make sure that the entire universe is there, so that you do not get out of it. On the other hand, a lazy construction, we have already seen that the 0 vector must belong to all the subspaces. So, just take that and construct a set W which consists only of the 0 vector, and that is also a subspace of V. These are the two extreme subspaces. Every subspace must have at least the 0 vector. So, take only that, and everybody must be a part of this. So, any other subspace, any subspace W of V which is different from these two is such that it must certainly be inside V because a subspace, and since the theta V belongs to every subspace, it must be like this. So, these are the two extreme subspaces, V the largest subspace and theta V is the smallest subspace. Now, what we want is somewhere in between, anything interesting will be in between. So, the main idea in analyzing a problem in vector spaces is, you take the full vector space V and try to chop it off into small subspaces. So, our idea will be to break or decompose the vector space V into smaller subspaces in such a way. Now, when we say smaller subspaces, we do not take like a butcher take a knife and start chopping the vector space, we must do it in a suitable manner, suitable subspaces. Now, in such a way, what do you mean by suitable? The analysis of our problem is easy in each such piece. So, we have broken the subspace into smaller pieces. Now, we analyze the problem in only each one of these pieces, we analyze the problem, and the way we break should be such that the smaller piece analysis becomes easy. And number 2, from this easy analysis of the smaller pieces, we must be able to patch up and get the full analysis. the smaller subspace analysis can be patched up to get the full space analysis. Most of our problems and analysis in vector spaces will be an endeavor to find such breaking. What are the mechanisms of such breakings? How should we break with reference to a particular problem? So, basically most of our course will be devoted to what sort of breaking of vector spaces is possible, what sort of vector space breaking we should look for, will they be available, under what conditions will they be available, if they are available how do we get them, and that forms the core of vector space or linear algebra analysis. We shall now begin looking at some examples of subspaces. The first we will start with some simple examples and move on to some very serious important subspaces that would be needed in our analysis. The first example we take is always in R3. This is the world in which we live in, the 3-dimensional world of R3. We take V equal to R3 and let us take W to be the set of all vectors in R3 which are such that they are of the form, the first component can be anything, the second component can be anything, but the third component must be the sum of the first and second components. Of course, all components must be real. So, we have the set of all vectors for which the third entry is the sum of the first two entries. Geometrically speaking, we can think of this the xy coordinate system, then it is just z equal to x plus y, it is a plane passing through the origin. So, what we are looking at is a plane passing through the origin, but let us do things algebraically first. Is W a subspace? Now, for this we have to verify three things. One, is it non-empty? W is non-empty because 0 0 0 plus 0 belongs to W, because this is of this form x1 is 0, x2 is 0 and x1 plus x2 is again 0. So, therefore, W is non-empty, the 0 vector belongs there. And then if you take two vectors in W, the next thing that we have to verify is that it is closed under addition. If you take two vectors in W, geometrically what does this mean? These two vectors are in this plane. If we take two vectors in the plane, their sum is also in the plane, that is what we are going to verify algebraically. X must be of this form x1 x2 x1 plus x2, y must be of the form y1 y2 y1 plus y2, and of course, all these xi's and the yi's belong to real numbers. Now, if I add these two vectors, what do I get? x1 plus y1, I will call it as alpha 1, x2 plus y2 I call it as alpha 2, and then I get x1 plus y1 which is alpha 1 plus x2 plus y2 which is alpha 2, where alpha 1 is x1 plus y1, alpha 2 is x2 plus y2. Now, since x1 and x2 are real numbers, x1 plus y1 is real number, x2 plus y2 is real number. So, these are all real numbers, and this is again where the third is the sum of the first two, it says x plus y belongs to W. Analogously, we see that if x is in W, alpha is in F, alpha x will be the vector alpha x1, alpha x2, alpha x1 plus alpha x2. which is again in double. And therefore, the first condition, this says W is non-empty, the second one we have verified shows that W is closed under addition, and the third one we have verified that W is closed under scalar multiplication. So, W is a non-empty subset closed under addition and scalar multiplication, which means W is a subspace of V. We shall see more examples of subspaces in the next lecture.